Buenas tardes y bienvenidos todos. Bueno, tengo el placer de presentar la conferencia de David Reitze. Para no alargarme demasiado, tengo las notas aquí como en la entrega de los Oscars, así que voy a proceder a leerlo directamente. Bueno, ya en 1913, Albert Einstein explicaba a su amigo Max Born que las pequeñas deformaciones del campo gravitatorio se transmiten a la velocidad de la luz como una onda. Esto era 2 años antes de que completara su teoría de la relatividad general. En 1916 publicó un artículo extenso sobre dichas ondas, artículo que luego revisó. No obstante, él mismo dudaba que pudieran ser detectadas jamás. Tuvo que pasar medio siglo hasta que aparecieron los primeros pioneros dedicados a comprobar la existencia de las ondas gravitatorias. Esos primeros intentos fueron calificados en muchos casos de excentricidades, cuando no de despropósitos. Precisamente las enormes dificultades de la tarea, de índole muy diversa, han hecho que la empresa de la detección de ondas gravitatorias haya sido una auténtica proeza. En 1975 coincidieron en Washington 2 personas que acabaron desempeñando un papel protagonista en el empeño. Se trata de Rainer Weiss y de Kip Thorne. Weiss había diseñado en detalle un detector basado en interferometría láser y durante una larga noche de charla convenció a Thorne de que el proyecto era factible. A Thorne se le unió el escocés Ronald Drever. Finalmente, bajo presión de la Fundación Nacional para la Ciencia Americana, la NSF, el grupo de Weiss y el de Thorne se vieron abocados a unar esfuerzos y con ello surgió LIGO, el Observatorio Gravitatorio de Interferometría Láser. Durante mi estancia en los años 90 en la Universidad de Syracuse, en Estados Unidos, tuve la suerte de conocer esas primeras vicisitudes de LIGO directamente de mano de algunos de sus protagonistas. Allí coincidí, entre otras personas, con Gabriela González, que actualmente es portavoz de LIGO. Desde esa perspectiva, me emociona aún más ver el camino que LIGO ha sido capaz de recorrer. Hubo que esperar hasta el año pasado para alcanzar una versión avanzada del diseño de LIGO. El 11 de febrero de 2016, David Reitze comunicó la primera detección de ondas gravitatorias en una conferencia de prensa seguida en todo el mundo, yo incluido. Lo comunicó con una bella sencillez. Sus primeras palabras traducidas al español fueron: señoras y señores, hemos detectado ondas gravitatorias. Lo hicimos. En esa conferencia estuvieron también Weiss, Thorne y Gabriela González. Representaban a una comunidad de más de 1000 científicos que son quienes componen en la actualidad la Colaboración Científica de LIGO, y entre los que se incluye el grupo Alicia Sintes de la Universidad de las Islas Baleares en España. Para darnos idea de la envergadura del logro, conviene hacer una comparación con la historia de las ondas electromagnéticas. James Clerk Maxwell predijo la radiación electromagnética en 1864. Heinrich Hertz detectó esas ondas en 1887, esto es, tan solo 3 años más tarde, en vez de un siglo después de la predicción, como en el caso de LIGO. Curiosamente, fue también un 12 de diciembre, como el día de hoy, cuando Guillermo Marconi estableció la primera comunicación transatlántica usando ondas de radio electromagnéticas. Era ya 1901. De forma similar, la detección de LIGO abre nuevos horizontes en las formas de explorar el universo y, sin duda, allana el camino para nuevas sorpresas científicas y tecnológicas. Nuestro orador, David Reitze, es el director ejecutivo de LIGO, ni más ni menos. Es profesor por la Universidad de Florida y está afiliado a Caltech, en el Instituto de Tecnología de California. Fue portavoz de LIGO de 2007 a 2011. Es fellow de la Sociedad Americana de Física y de la Sociedad Óptica de Estados Unidos. Es experto en espectroscopía láser y en interferometría láser gravitatoria. Su currículum es extensísimo y, sobre todo, ha tenido un impacto que podemos calificar ya de decisivo en el desarrollo de la ciencia. Hoy contamos con el enorme privilegio de tenerlo presente aquí, gracias a la Fundación BBVA, para transmitirnos cómo LIGO ha conseguido oír audazmente aquello que nadie había oído antes. Cuando quieras.
Gracias. Muchas gracias. It's a great honor for me to be here. First of all, I'll tell you, this is the first time that I've spent any time in the beautiful city of Madrid, and I really love it. I will be coming back. I'm going to tell you a story, and the story begins 1.3 billion years ago, give or take. And it is a story of two black holes colliding with one another. We're going to fast forward and skip most of those 1.3 billion years and come to 100 years ago, almost 100 years ago, when Albert Einstein postulated a remarkable theory of gravity called the general theory of relativity. This picture is an excerpt from the paper, and that equation at the bottom is a very famous equation if you work in general relativity. It's something called the space-time metric. Right? I'm not going to get too deeply into the theory, but I will talk a little bit about what it means and why it's so important. So let's start with special relativity. Special relativity is Einstein's first theory of relativity, and perhaps the most famous equation in the world comes out of special relativity, E equals mc squared. But there's a second set of equations that come out of special relativity, and that's the equation on the bottom, this one right here. And if you look, you'll see two variables in that equation, actually three. You'll see x prime, you'll see x, and you'll see t. All right? X prime is a measurement of displacement, or it's a location. All right? X is also a measurement of location. T is this fundamental quantity we know called time. Now, the second equation is remarkable because it mixes space and time. It says that one observer moving at a certain velocity measures time and space differently than another observer. So these two equations are remarkable. The first equation, E equals mc squared, mixes energy and matter, or energy and mass. Right? And the conversion factor is that c squared. The second equation mixes space and time. So Einstein took four fundamental quantities, energy, mass, position, and time, and at the end of the special theory of relativity, we just had two quantities because space and time were interchangeable, matter and energy were interchangeable. General relativity is much more complicated, all right? And this is the equation for general relativity. It's equation that mathematically is more difficult to solve, which is why it took him so long to do it. It was actually a theory that a large number of physicists took a long time before they understood. I'm not going to explain this equation in any detail, but I will tell you that this side of the equation is space and time. This side of the equation is matter and energy. And this over here is a coupling constant. And that coupling constant is very important, and you'll see why very soon. Now, I apologize for the notation. Historically, this G is the Newtonian gravitational constant. This is called basically the Einstein tensor. They're not the same thing, but physicists sometimes use the same letters for different terms here. All right, so what does this equation really mean? All right, it means the following. It means that space and time are equal to matter and energy times a constant. And that constant is 8 pi g over c to the fourth. If you calculate the value of that constant, you come up with a number that is very, very small. It's about 10 to the minus 43, all right, or 0 with a decimal point, 42 zeros, and a 1. It's actually a 2. So what this says is it says that it takes a lot of matter and energy to change space and time. Let me draw a picture for you, all right, because I think this picture explains much better general relativity. So what you see there is you see the sun, you see the earth, and you see a green grid, all right, and you see that that green grid is deformed, all right. Pay attention first just to the sun and the earth. All right, before Einstein explained gravity through the general theory of relativity, we had Newton's laws, Newtonian mechanics, which was a very powerful and predictive theory that said that if I have two objects that possess mass, there's a mutual attraction between them. That attraction is proportional to one mass times the other mass. In this case, the mass of the sun times the mass of the earth. It's inversely proportional to the distance squared. So if you measure the distance from the center of the sun to the center of the earth, you take that number, you square it, you divide it into the masses, and you get, and then you multiply by g, the gravitational force constant, you get the force of attraction. And this was also a remarkable theory, even though it's 400 years old. It predicted orbits. We could use this to predict the way the solar system worked, to predict a lot of classical mechanics. But it had one flaw, and the flaw, even Einstein, or even Newton knew what the flaw was. The flaw was that the interaction between those two bodies happened instantaneously. And one of the things that special relativity tells us is that there's a natural speed limit in the universe. It's the speed of light. No information can travel faster than the speed of light. So Einstein rectified that problem with general relativity by saying, all right, there's no magic force between these two massive objects, the Earth and the Sun. In fact, what's happening is the sun, all right, now we'll pay attention to the green grid. The sun is a big massive object sitting in space. All right, since I can't represent space as 3 dimensions, I'm only representing it as 2 dimensions here. When I'm far away from the sun, when I'm far away, space is flat. In other words, it looks like a coordinate system that you learn in geometry when you're in high school. When I get close to the sun, the mass of the sun warps geometry. It curves space-time, and that's represented by that curvature that you see, that dimple, that big dimple in the green grid. All right. Now the Earth also has mass, not as much, so it also warps space-time, but in fact it's not warping it as much, so the dimple is much smaller. All right. And again, because that coupling constant is so small, it takes a big mass like the sun to even change the geometry a little bit. Now, how does the Earth know the sun is there? The reason the Earth knows the sun is there in general relativity is because of the fact that the space-time around the sun is distorted. So the Earth is actually trying to move in a straight line. But for it, a straight line is actually a curved line because it's sort of sitting in this bowl here defined by the sun. And if the sun were to disappear, if it were to just vaporize and go away, all right, the geometry of space-time would change, but it would take basically the travel time of the speed of light, about 8 minutes before the Earth saw the space-time change. All right, so this is fundamentally general relativity. Basically, it says that space, all right, tells matter how to move, and matter tells space how to curve. All right, where do gravitational waves come into this? Well, they come naturally out of the theory. So if I have two objects, in this case, these objects are black holes, all right, even the sun and the Earth would do this too, and I orbit them around one another, basically because the space-time geometry is changing, these gravitational waves are rippling outward. So what's really happening here is these two black holes are orbiting around one another, and as they orbit around one another, their orbit decays because they're radiating energy away in the form of gravitational waves, all right, and eventually they collide together. Now that picture that I just showed you, the movie that I just showed you, is a nice conceptual way to represent gravitational waves. But if you're an experimentalist, if you're trying to measure gravitational waves, you have to ask yourself, what is it that you're really trying to measure? And the answer is something called a strain, all right? So a gravitational wave, physically, is a change in length per unit length. So this is a very important equation for a couple of reasons. You'll see why in a minute. All right, delta L, that quantity delta L, is a displacement, all right? It's how much 2 points move or 1 point moves relative to another point. L is the separation distance between the 2 points, all right? So immediately, this suggests something to you. It suggests that if I want to measure, if you want to build a device to measure gravitational waves, you want to make your baseline, the distance between you measure the points, as far as possible, because you want to make this quantity as small as possible. The smaller that quantity, the more able you are to measure gravitational waves. All right. Now, to give you a feel for this, I'm going to actually show a cartoon that, in fact, is a real representation of gravitational waves. So suppose a gravitational wave were traveling out of the board here, or out of this screen here, towards you. What would you see? What would space be doing as a function of time? And the answer is this. So focus on the graph on the left. You'll see that what it's doing, it looks like it's breathing, all right? But in fact, what's happening is on every half cycle, the x-axis, the horizontal axis, is getting longer, while the vertical axis is getting shorter. And that repeats itself on the next half cycle. The vertical axis gets longer, while the horizontal axis gets shorter, all right? And the further you are away from this sort of arbitrarily defined point here, the bigger that change is, all right? So this is the physical representation of a strain. So if I want to measure, all right, a gravitational wave, all right, I want to be here and here because I see a bigger effect than if I'm here and here. The closer I am to that crossing point, the smaller the delta L, because the delta L is proportional to that baseline. And this is just a different polarization of the gravitational wave. So gravitational waves come in two flavors, and this is just pictorially how they would look if they were coming at you. Now, the important point here, again, it comes back to that constant that I talked about earlier, that coupling constant, is that this greatly, greatly, greatly exaggerates the size of the effect. Even Einstein himself knew this. This is an excerpt from the paper in which he predicted gravitational waves. And don't worry about this equation. I'll just point out that A in our notation is this delta L over L. So this is the amplitude of the gravitational wave, right? And I can't read German, but I can translate it in Google. And so what this says here is then A must have a virtually vanishing value in all imaginable cases. So this is Albert Einstein saying to any physicist who wants to try and measure this, don't bother. You won't be able to. And probably that was true with the technology that he had at the time. But if we fast forward 100 years, we have better technology, and that's how we achieve this. So let me give you a sense of how small these waves are. All right, so I'm going to do a Gedanken. This is what Einstein would call a thought experiment. I'm going to take two objects, I'm going to separate them by about 1 meter, and I'm going to make them heavy, 1,000 kilograms. I'm going to spin them around 1,000 times per second. Now, I wouldn't do this in my own home because the objects might fly off and damage things, but this is a mad scientist, and he decided to do that experiment. He was smart enough to move far away, so he moved about 300 meters away, a third of a kilometer away. If you do that calculation for this source, you get delta L over L is 10 to the minus 35, 0.34 zeros and a 1. That is a tremendously small number. And I, as an experimentalist, would be depressed, pessimistic about measuring this. But we can do this experiment in space. In fact, nature does it all the time for us, it turns out. All right? Instead of using massive objects that are 1,000 kilograms, let's look at astrophysical objects that are much more massive. All right, so let's take 2 neutron stars. All right, these are neutron stars are basically the cores of supernova. Once a star explodes, if the star has the right mass, what's left over after all of the outer shell of the star blows off is a very compact, very dense object. So these are made of pure neutrons. These are neutron stars. They're about 1.4 times the mass of the sun. And they are very compact. The diameter of these stars is about 20 to 25 kilometers. Now, turns out when nature puts these stars together, all right, nature spins them around 1,000 times a second. All right, naturally, that's their orbital frequency when they are very close to one another. And if you do the calculation, you come up with a number that's slightly bigger, about 14 orders of magnitude bigger, 10 to the minus 21. That is still a tremendously small number, but it turns out that using interferometry, you can actually measure that. And that's what LIGO does. So now, all right, now I've told you a little bit about general relativity, I've told you a little bit about gravitational waves, and I've told you a little bit about how difficult it is to detect them. So now what I want to tell you is how LIGO works, what LIGO is, and how we do detect them. All right, so as Guillermo said, I'm based at Caltech, and I work with the LIGO laboratory, which is a group of about 190 scientists and engineers. Engineers are a very important part of LIGO. We are based either at Caltech, at the Massachusetts Institute of Technology, or our observatories. One is in Hanford, Washington, so that's in the northwest corner of the United States. The other is in Livingston, Louisiana. If you've ever been to Baton Rouge or New Orleans, you were actually not that far from our Livingston Observatory. We are the group of people that built the detectors that operate the observatories. There's a much larger group of people called the LIGO Scientific Collaboration, of which Professor Alicia Sintes from the University of Balearic Islands is a member, which does the science of LIGO, so looks at the data and tries to find these signals. So this is a very big endeavor. There are about 1,100 scientists that are involved in this. All right. And to give you a sense of scale, all right, this is what one of our observatories looks like from the air. So this is the Livingston Observatory. The yellow arrows are 4 kilometers long. So remember I said that delta L over L is an important quantity. Well, the L in this case is 4 kilometers. So if you do a little math in your head, that will tell you that the delta L that we have to measure is about 10 to the minus 18 meters. All right, and to put that in perspective, 10 to the minus 18 meters is about 1/1000th the diameter of a nucleus of an atom. So we are trying to measure changes, all right, over this long baseline that are, excuse me, 1/1000th diameter of the nucleus of an atom. To put it in perspective, those are automobiles, so these are cars here. So you get a sense of scale. Here is the identical observatory in Hanford, Washington. All right, it's exactly the same. The only difference is that it's in a different location. It's about 3,000 kilometers away from Livingston. All right, so now let me talk a little bit about, and this is a key part of my presentation, about how we do this experiment. How do we build these observatories to make them so sensitive? We use a technique that's called interferometry, and interferometry has a very storied history in gravitational waves. The first time interferometry was actually used by Michelson-Morley, it was used to disprove a theory that there was a preferred direction in space, something known as luminiferous ether. It's very hard to say, actually. Let me explain how it works. All right, so this is a laser, and in our case, this is a very, very special laser. We worked very hard to put it together. This is something we call a beam splitter. So the laser produces a laser beam. That piece right there basically takes the laser beam and divides it equally in two. It reflects half of the laser beam up to that arm right there, or that mirror right there, and it lets the other half transmit to that mirror right there. And basically what we're trying to do is measure the distance between the beam splitter here and that mirror, and the beam splitter here and that mirror. So if you think about the picture of gravitational waves where the strains are moving like this is actually an ideal geometry to make that kind of measurement. All right, this is a screen that will be used to actually measure, at the end of the day, measure the light that comes out. So I'm going to start a movie, and the movie is going to show you how interferometry works. Before I start it, last thing I need to say. The laser that we use produces very pure laser light, and it has a wavelength of about 1 micron, so 10 to the minus 1/1,000,000th of a meter. All right. The nice thing about light, and laser light in particular, is that it's very pure, and a wavelength of light is almost, in fact, it is the best ruler that you can have. So we use these rulers in interferometry. Let me start the movie. You'll see 2 beams come out. There they get split. and you see they're color-coded. And pay attention to the waves. So this is the X arm, all right, and it's got a yellow wave associated with it. And it comes back with the Y arm, that's that arm. And when it recombines, right now, the waves interfere destructively, so no light comes out. So all the light is actually coming back here. But then, as a gravitational wave passes, it moves one arm in one direction, the other arm in the other direction, and it changes the interference pattern so that you go from a dark fringe where there's no light to a bright fringe. All right. And basically what you've done, what the interferometer is doing, and it's quite remarkable, is it's taking the stretching and compressing of space-time, all right, that you measure along the different arms of the interferometer, and it's turning it into basically a time-dependent light field that you can record. And instead of having a screen there, we put something called a photodiode, which is basically a little receiver. So what this interferometer does, it's like a radio, all right? It picks up the signals of gravitational waves and transduces them and turns them into photocurrent, into light, which then gets read out as photocurrent. So basically you can record gravitational waves, all right, with this device, and I'll come back to that. All right, now I have to point out, again, I exaggerated the size of the effect. So in the movie, the waves were actually sloshing back and forth. They were moving by about one wavelength. In our case, because of the sensitivity of the instrument we need, we are actually capable of measuring the shift in the wavelengths by about 1/1 trillionth. So that's 10 to the minus 12, actually even a little bit better. So we see very, very tiny displacements. All right, and in order to do that, we have a lot of wonderful technology, not just the lasers, but also the optics. So let me walk through some of that. But first, let me tell you the challenge, why this experiment is so hard, all right? What you have to battle against to do an experiment like this. All right, so here's another picture of our interferometer. Again, the laser, the beam splitter that sends one light beam this way, one light beam this way. And here now is what I called the photodiode. So it's the receiver. It takes the light and turns it into current. All right, the first thing you have to worry about is the Earth. All right, so the Earth is moving. You don't feel it. Although here in Madrid you might, as a truck goes by or a train goes by, the Earth vibrates. All right, those vibrations turn out to be about 1 trillion times larger than our level of sensitivity. So we have to basically isolate the interferometer to a level where we get rid of all those seismic seismic perturbations. So earthquakes affect our interferometer. If somebody is walking by the interferometer, we can actually measure that. We can measure the footsteps just by looking at the signal that comes out here. It's that sensitive. All right, obviously we shield the interferometer so people don't walk by there. All right. The next thing that can happen is actually a technological thing. If you're a laser physicist, you worry about this a lot. Everybody believes that lasers are the purest form of light, and that's true, but they're not perfect, all right? And over the course of a day, an hour, a minute, a second, even fractions of a second, the wavelength of light can change, all right? And if the wavelength of light changes as a function of time, all right, what happens is the measurement, basically, as the waves are changing, it changes the interference pattern here. So that looks like a gravitational wave signal. So we have to work very hard to basically stabilize the wavelength and the amplitude. If the power changes, that's a problem for us too. Right? So we stabilize our laser to a level of about 1 part in 10 to the 22. So in other words, the frequency change over a given time period is about 1 part in 10 to the 22. All right. The third source of, the third source of noise is fundamental, and it's really an interesting physics problem in its own right. And it's called quantum noise. All right. And this has to do with the nature of light itself. All right. So light, like most of the physical world, is actually a quantum entity. Right? We can think of it as a wave, and when I showed you the interference pattern, the interferometer, it looked like a wave. But it's also photons. It comes in discrete units, packets of light called photons. And this was something, by the way, that Einstein recognized. And these photons, because of the nature of light generation and light generation, the photons arrive at random times. All right, so if a photon is traveling this path and a photon is traveling this path, all right, and because they're randomly generated, they can actually hit the photodiode at different times, and that itself looks like a change in the interference pattern. So this is something called, physicists call it shot noise. Again, it's a fundamental property of the nature of light that in any given light field, all right, the arrival time of the photons is somewhat random. Now you can beat that by turning up your laser power. It turns out that the randomness is proportional to, inversely proportional to the power. So if you turn up the power, you can suppress the randomness somewhat. All right, and so that's what we do. Our laser is about 180 watts of laser power. However, there's another kind of noise, all right, which is in some sense the complement of shot noise, and it's basically photon pressure. So light, because it has energy, it also has momentum. So again, coming back to the fact that light is quantized, that it comes in discrete packets called photons, when those photons hit the mirror, because they're hitting at random times, they're actually pushing the mirror. All right, you might say this can't be a big effect. I mean, we have these big mirrors. The mirrors are 40 kilograms, so they're very, very heavy mirrors. All right, it's big enough because, remember, the size of the signal we're trying to measure is 10 to the minus 18 meters. So this is a real problem for us. And unfortunately, you have to turn the power down to be able to get rid of that noise source. So there's a sweet spot, if you will, a magic power. Actually, you can calculate it. It's called the power standard quantum limit, where you operate your interferometer to get the least noise from shot noise and the least noise from photon pressure. All right. There's also a fundamental noise called Brownian noise or thermal noise. Again, something that Einstein first thought about. He actually calculated Brownian noise. All right. And this has to do with the fact that these mirrors are at a finite temperature. All right. And any object that's at a finite temperature, all of the atoms, all of the molecules in the mirror are moving, and they're moving randomly with a certain amount of energy that you can calculate using something called statistical mechanics. And in our case, what's happening is those mirrors are actually, the surface of the mirror is actually vibrating. It's vibrating at a very specific frequency, but there's a little bit of vibration there, and that turns out to be something that you have to design your interferometer to try and avoid. All right, we do all that. The last thing you have to worry about is scattering, something we call residual gas scattering. All right, and residual gas scattering happens when a light particle, a photon, hits a molecule. So in the atmosphere, we have oxygen, O2, we have nitrogen, N2, we have water, H2O, got lots of different kinds of molecules. And when light hits those molecules, it changes its phase. In other words, it actually delays the light, and that looks like a change in phase, which would again corrupt our measurement. So the way we get around this problem is we put this whole interferometer in a big vacuum. So let me walk through some of the sort of pictorially, some of the detector. So this is a picture of the inside of the corner station, so those big buildings that I showed you earlier. And the laser is over there. There's a picture of the laser. You see that people who work with the laser basically have to be very, very clean because the laser is so powerful that any contaminants, any particulate matter can actually cause the laser to be damaged. Here's the beam splitter, right there. This is one arm. So if you go this way down 4 kilometers, you get to the end mirror. If you go this way, you get to the other end mirror. There are lots of other, and this is a vacuum system, so this is all under very high vacuum to get rid of that residual gas scattering. There are lots of other mirrors and optics in here that I'm not talking about, but they're all essential in order to be able to get the light beam and to get the level of sensitivity that you're trying to get. Okay, so let me talk just for an instant about some technology. So we use mirrors, I told you, that are 40 kilograms. Those mirrors are remarkable. They're basically the state of the art. They're made of something called fused silica. And they're made of the same kind of fused silica that whenever you whenever you do a Google search or do something on the internet, the light gets converted and sent through a fiber. So it's very, very pure fused silica, and it's very, very expensive. All right, this is actually the mirror. So this is the mirror before it's suspended. This is the mirror in the interferometer, actually, before it's installed. But this is really, I would say, one of the key features that makes LIGO work so well. All right, here's the mirror. You see there's another mass, there's something up here, and there are a couple of more stages up here. Each one of those stages is connected to one another by wires, except for these stages, which is also connected by optical fibers. Right? And the reason for that is we use a tried and true method of physics called harmonic oscillators that allows us to suppress that motion. So this is where you get that factor of 1 trillion suppression there. In addition, above that, we have one more level of suppression. We call it active seismic isolation. So in order to be able to keep this mirror quiet and all of this quiet, we have seismometers that are on the ground. So seismometers measure earthquakes, but they also work for LIGO. And those seismometers basically measure the ground motion and then feed back and correct for it. So the example I'll give you is if you drive a nice car, perhaps like a Mercedes-Benz or a BMW, it has active suspension. So when you drive over a bumpy road, all right, the wheels are doing this because the road is doing this. But you sitting in your car are having a nice smooth ride. That's because there is basically a sensor system that reads out the motion of the wheels and then feeds back to the platform of the car so that you don't feel it. We do the same thing, but we do it about 1,000 times better than Mercedes-Benz does it. The vacuum system is a remarkable piece of technology. So this is a 1.2 meter diameter tube. And at this point, let me step back and say, you might be wondering what this has to do with black holes and gravitational waves. Well, it turns out that without the vacuum system, you have no hope of measuring gravitational waves. So there are roughly, if you calculate the volume, there's 9,000 cubic meters, 9,000 cubic meters of nothing. Literally, we pump it out. There's 30,000 square meters of surface area. All right, so this is 4 kilometers long. There's another one. All right, and so there's 8 kilometers of beam tube, and then we weld them together. Making this was a really tour de force in engineering, and we pump it down to about I believe it's 1/10 of an atmosphere. All right, which is the level that we need to be able to do this, and we do that at each observatory. Now I will tell you that if you're an experimental physicist, you know that when you make vacuum systems, they naturally leak. Occasionally there will be a leak. And this vacuum system did have a leak at one point, and it had a leak that was equivalent to a 10 micron, so that's basically 1/100,000th of a meter hole. And here's a question that you can ponder for yourselves. How would I find a hole 10 microns in something that is 30,000 square meters of area? It is not easy. It really isn't. But there are techniques, and we were able to do it. Now, I'll point out that there are these covers here. They're concrete covers that are very important for protecting the beam tube. This is a stainless steel beam tube from the environment. They're also important for protecting it from human beings. So this was a car that actually, unfortunately, was driving without its lights on in the middle of the night. Why they were driving there, I don't know, but basically they collided. All right. So now I've given you, I hope, a feel for how we try and do the interferometry at a very sort of high level. So now let me talk about the detections and why they're so amazing. So on September 14th of 2015, we had just started operating our interferometers. And in fact, the truth be told, we weren't even officially in what we would call a run mode. We were in something called an engineering mode, which means we were testing the equipment, making sure everything was right, but we were collecting data, and the data was scientifically valid. So we said if there was something interesting in the data, we would be able to look at it. Right? And what we saw was this. So now we're going back in time 1.3 billion years. I'm going to show you a simulation. Before I show you the actual data, I'm going to show you a simulation of what we saw. All right? And this is not a Hollywood movie. This is actually a simulation that is produced by solving that equation that I showed you earlier, the general relativity equation, basically for this system of two black holes. Now, there are two black holes in this picture. One, the smaller black hole, is almost 30 times the mass of the sun. And to give you a sense of scale about how compact and massive these objects are, all right, it's about 170 kilometers in diameter. The second, the big guy, the bigger black hole, is 36 times the mass of the sun and about 210 kilometers in diameter. One brief detour through black holes. Black holes, it turns out, are also something that are predicted naturally from general relativity. And in fact, they're in some sense a very simple object. Right? Black holes are defined by only three things, and in fact, astrophysically, only two things. They are defined by their mass, how much mass, in this case 20 times or 36 times the mass of the sun. They're defined by their spin. In other words, if I were to take the black hole and spin it around, which naturally happens, there's a natural frequency of the spin, we call it the spin parameter. And then there's a third quantity, charge, like electrical charge. Turns out that astrophysically, we don't believe that charge is fundamental for astrophysical black holes. So it's really two quantities, mass and spin. Now, the reason those black holes are black is because when a black hole is formed, it's formed in such a way that there's a massive crunch of matter. So if you have a star that explodes a supernova, if that supernova is massive enough, and if the core of what's left behind is massive enough, it doesn't form a neutron star, it forms a black hole. Basically, the gravitational attraction is so strong that it just keeps collapsing into itself. All right, so much so that there's a point, all right, called the event horizon, all right, where no light can escape. And so everything, all right, that's inside this black period is basically inside the black hole. Now, interestingly, even though the black holes are defined by their mass, they are pure space-time, all right? Basically, this is pure curvature, all right? So the mass, all the identity of the mass, all the information that's contained in the mass, what kind of elements it is, it's all gone, and it just turns into space-time. Okay, so now you put two of them together, all right? And now I'm going to show you a movie. Again, it's a simulation here, and the movie's slowed down by about a factor of 100. The stars behind it are merely there so you can keep track of what the black holes are doing, all right? All right, so the black holes are spinning around. The reason the star field is moving is because of the bending of light, because remember, light travels along the same path as the geometry of space-time, and space-time is very bent, it's very warped there. All right, so these black holes are orbiting around one another, again, very slow motion, and you'll see they're getting closer together. They're getting closer together, speeding up as they get closer together. Eventually, their event horizons touch and merge, and at the very end, you probably saw a little bit of a ripple. And that little bit of a ripple was the final burst of gravitational waves coming out of here. All right. What's left behind is a bigger black hole. So what you just watched was sort of the last tango or the final ballet of these two black holes merging into one another. They disappear, their identities disappear, and they give birth, if you will, to a bigger black hole. Now, the bigger black hole is 62 solar masses. And I should point out, in fairness, that the numbers I'm quoting are approximate. There are error bars. We don't know exactly. All right? And that 62 solar masses, all right, is not the same if I take 29 and 36 and add it together, I get 65. What's left over is 62. So 3 solar masses disappeared. What happened to those 3 solar masses? Gravitational waves. So that final burst that you saw basically was the conversion of 3 times the mass of the sun into gravitational waves. And it happened in about 0.2 of a second. So I can calculate, we call it a luminosity, you would call it a power. In that brief instant, all right, this object, this merging object, which we observed on September 14th, was about somewhere between 30 and 50 times as bright as the entire universe in the electromagnetic spectrum. So this is a mind-bogglingly violent event. All right, this is the data. This is actually what we saw. All right, and this is beautiful data. When I saw it, when many others in the collaboration saw it, we just swooned because the data is so perfect. You can see it in the raw signal almost. And I won't go into this too much. Suffice it to say that the waveform that you see here, all right, looks very much like the movie I just showed you. What happens is as the black holes are dancing around one another, the frequency is increasing because they're spinning around each other faster and faster, and then they collide and merge together, all right? And then once they collide and merge, there's one big black hole, and it's not doing anything. It's just spinning around, so the signal disappears. And you can see that there's a slight offset here. At Livingston, the signal came in a little bit sooner, about 7 milliseconds sooner than we saw it at Hanford. And that information is important, as we'll get to later. All right, coming back to the delta L. So the delta L for this particular wave, all right, was 4 times 10 to the minus 18 meters. It's about 2/1000ths the diameter of a proton. All right, so this massive black hole, these two massive black holes colliding with one another at about, they're moving at about half the speed of light when they collide. All right, propagate 1.3 billion years away and produce a signal that we can register as 2/1000ths the diameter of a proton. That is pretty mind-boggling. All right. We actually saw 3 events. Well, we would say 2. We're very conservative in the gravitational wave field. All right. We do a lot of statistical analysis to convince ourselves that we've actually seen a signal, and I'm not going to talk about that. But we saw this first event, which was what I just showed you. All right. We also saw a second event. We call it the Boxing Day event. It happened on December 26th. All right. And then there was even a third event, all right, that statistically wasn't as confident for us, but we believe that it was a black hole, so we're going to call it a candidate, a black hole merger candidate. All right. Now I want to come back to this idea that interferometers are transducers or radio signals, right, that you can actually, from the black hole signal that you get, the signals of these black hole mergers that you get, that you can actually hear the signal. So I'm going to play it for you. So these are the events that we heard. All right, so this is December. That's September. Now I'm going to increase the pitch. It gives you So what you've just heard are the sound of black holes colliding with one another. Oops, let me get away from that for a second. All right, and that pitch that you hear, that whoop, that's called a chirp. And there's a huge amount of information in that chirp. All right, so it's remarkable that because of the frequency that these black holes merge together, that we can play them back as sound. I think that's quite fun. All right, when we made this discovery and we made the announcement on February 11th, immediately there was an amazing amount of press that we got. In fact, I was quite stunned by the amount of attention. We knew this was a big result, but we didn't realize how big it was. And so gravitational waves have shown up in popular culture. This is one of my favorite cartoons, which appeared very soon after we made our discovery, and I will read it for you because I think it's quite funny. All right, so this says, obviously we can't see these waves. The only way we know these waves are real is by using another extremely sensitive device which detects scientists having feelings of emotion. All right, and you can see here there are a bunch of scientists. All right, this guy right here has basically gotten really excited about a gravitational wave. This guy over here is really excited about his lunch, cheese salad sandwich. All right, more interesting to me is the fun fact. Scientists' emotional reactions are also the fraction of a width of a proton. I can tell you that that is not true. It turns out you can now buy gravitational wave fashion. All right, so this is a company that makes a dress. All right, And it's about 200 euros, a little bit less than 200 euros. You can go online and buy it. They also make ties. So I'm wearing a gravitational wave tie. So these are the gravitational waves. In New York City, literally a month after the announcement, so this would be in March, a friend of mine sent me this picture. All right, this was in the metro, in the subway in New York City. Scientists found gravitational waves in outer space. If only it were that easy to find an apartment with a walk-in closet in New York City. All right, I've never lived in New York City, but I never want to if this is how hard it is to find an apartment in New York City. And the last thing I'll show you, I just show you because in the United States, this is a very popular television show. I don't know if it is over here, but this is Sheldon Cooper, and he's got a gravitational wave shirt on. So anyway, so there's been a lot of fun popular culture with this. 1 year after our discovery, this would have been on September 14th, 2016, a very clever postdoc decided to do this. So here's the sound. So that is the first bona fide gravitational wave song that I've heard. Now I can tell you that there are more serious composers that have contacted us about using the gravitational wave chirps in their compositions, and I'm sure they'll be better than this. All right, let me close. The last thing that I want to talk about, I think, is probably the most exciting thing. We've made this discovery. It's been a big deal. But the future is really where we want to go here. So, and it's astronomy, all right? So gravitational waves are unique probes of the universe. Everything we know about the universe so far comes from really 4 fundamental types of measurements, all right? First is telescopes, all right? So we build these big telescopes. This is a 30-meter telescope that hopefully will be operational in 2022, and it looks at light. There are other kinds of telescopes that look at X-rays, gamma rays, radio waves, millimeter waves, but basically it's all electromagnetic. The other thing we do is we collide subatomic particles together at relativistic speeds to study the microscopic universe, and we do that at the Large Hadron Collider. So I'm sure everybody's familiar with the discovery of the Higgs boson that happened a few years ago. All right, very important way of getting information about the subatomic world that actually tells us a lot about the way the universe works. Third way, perhaps not as well known, but nevertheless very important, neutrinos. So this is a picture of the Super Kamiokande Neutrino Observatory, which is basically a big tub of water with a lot of photo collectors, photomultiplier tubes in a mountain in Japan. Finally, there's cosmic rays, all right, that the universe produces very, very energetic protons, which can then decay and produce cosmic rays, which we can measure using devices in very remote places. This is in Chile, I believe. Okay, now, all of these things are tried and true, and we've been doing them for many, many years. Gravitational waves are fundamentally different from all of this, and so they're a new way to look at the universe. And let me give you an example of what we've done with these detections in the past year. So one of the most fascinating objects, I've already talked about it, is a black hole. The way we know about black holes is from something called a low-mass X-ray binary system. You have 2 stars, one of them a black hole, or was a star, but now it's a black hole, another star that's in close proximity, that's still a live star, but it's so close that the matter from the star can actually get sucked off and basically accrete onto the black hole. And as it does so this is basically hydrogen or whatever the star is burning at the moment, could be helium, all right? And it comes, and because the black hole is spinning, all right, it swirls around, and the closer it gets, the more energetic it becomes, and it emits X-rays, gamma rays. And it basically, by the time the matter gets to the event horizon of the black hole, it's very energetic. And you can study this using X-ray astronomy, and X-ray astronomers have been doing this for the past 40 years. All right. And here's what they have discovered. All right. These are the 22 or 23 black holes that have been discovered using X-ray astronomy by studying those low mass binary systems. And this is the solar mass, we call it a spectrum, basically. This is 0 solar masses, this is 70. And you can see that the X-ray studies have identified a lot of what I would consider low stellar mass objects. Compare that with LIGO. LIGO has discovered, well, here's the first one, here's the second one, and here's that candidate. You can see immediately something fundamentally different. First of all, these guys are all in our galaxy. These guys are all very far away, billions of light, in the case of this one and this one, about 1.3 billion light years. This one even further, about 2.5 billion light years away. The masses of these guys are bigger than the masses of these guys, all right, which means we're looking at a different kind of black hole. And in fact, one of the things we want to understand is how black holes form and how black hole binary systems form. And LIGO could give you a clue to that. But I think the thing I really want to emphasize here is that this is 40 years of X-ray astronomy. It took 40 years of careful study to find that many black holes. It took us 4 months to find, I would say there are 9 black holes there. Now, admittedly, every time we see a black hole merger, 2 of those black holes disappear and 1 is left behind. Nevertheless, you learn a lot about the initial black holes and the final black hole that's left over. So basically, in 4 months, we've increased the number of known black holes by approximately 30–40%. Now, in fairness to the X-ray astronomers, the precision with which we measure these masses is much less. These are very well-studied objects, and they're more precisely known than these are. But nevertheless, as LIGO continues to operate, we're going to see more of these binary black hole systems, as well as other kinds of sources, binary neutron stars, for example. And when that happens, we'll be really the ones that can do the most prolific black hole physics. All right. Why do we want to use LIGO as an astronomical observatory? Well, the idea is that you can actually, let's forget about black holes for a minute and let's go to binary neutron star mergers. So this is another picture that I showed you earlier. This time they've collided together. And because binary neutron stars have mass, have matter in them, when they collide, they do so with a tremendous bang electromagnetically. So these produce, we believe they produce gamma rays, they produce optical, they produce radio. So if you can see them in different kinds of modalities using these techniques that I showed you before, not just gravitational waves, but visible light, radio waves, neutrinos, X-rays, you get a more complete picture of this kind of event. And so this is called multi-messenger astronomy, and it's really, I think, where the future is going to lie here. And the way we do it is we use the fact that we have multiple detectors. So one interferometer is not like a telescope. This is a very important point. It's a very poor localizer. So if one interferometer detects a gravitational wave, you don't know where it came from. If 2 interferometers detect a gravitational wave, you have some indication of where it came from. If 3 interferometers detect a gravitational wave, you have a better indication. It's just like triangulation. Before there was GPS, your cell phones used to know where you were because you would triangulate the signal from your cell phone to 3 different cell phone towers. That's in fact what we're doing here. We're just measuring the time difference between the signals when it arrives here. And in fact, it turns out 3 interferometers isn't enough. But basically the idea is that if you can do this quickly, if you can get these signals quickly analyzed, you can then send, we call them alerts or telegrams, to your astronomical partner saying, hey, we think we saw an event over there or over there. Point your telescopes that way and tell us what you see. And do it quickly because we want to catch these guys in the act. All right. So to do that, you need even more than 3 interferometers, and I'll show you why in a minute. So this is the network that's now under construction. So there are the 2 LIGO detectors. This is a detector that's in Italy, outside of Pisa, called Virgo. Same kind of detector as what I showed you with LIGO. It will be operational in about 3 or 4 months, we hope. CAGRA, This is a detector that's in Japan. In fact, it's right next to the Super K, that neutrino detector I showed you. It will be operational in, we hope, 2019 or 2020. And we have a detector now that's under construction in India. It's actually just gotten started, so it'll be about another 8 or 9 years before it's operational. All right. Why do you want all these detectors operating? There are many reasons, but let me give you the punchline. So the event that we saw on September 14th, we actually were able to quickly localize that event, all right, using fast analyses, all right, and say where it came from on the sky. So this is a projection of basically the entire universe, the sky, into sort of a sphere there. So you would be at the center of that sphere. This is the Milky Way galaxy here, just to give you some perspective. And those colors represent the positions, the probable positions of these black holes, this black hole that we've discovered. And you can see that they're not very well localized. In fact, astronomers look at this and they go, oh, that's hard to see. I can see something that's much, much better than that. So it's very hard for them to cover all the ground. So let me do a simulation now and say how much better can we do. And this is with Hanford, Livingston, and Virgo. And you can see there are some places, so these ellipses are basically the size of the localization, how well we can localize something. There are some places that are good, there are some places that are very poor. And we know the reason why. If I just add one more detector, if I add a fourth detector, say India, this cleans up dramatically. And now astronomers look at this and they say, oh, this is great. I can point my telescopes and I should be able to cover one of these little ellipses in a very, very rapid period of time and see gravitational waves, optical, radio, gamma rays, etc. So this is really where the future is going to be. And I should point out that gravitational waves are not just what LIGO detects. They come in all kinds of different wavelengths. There are longer wavelengths that are minutes to hours. Ours are sort of milliseconds. There's a project that's under development by the European Space Agency called ESA that will measure gravitational waves from space, looking at intermediate mass black holes. There's something called pulsar timing. I won't go into the techniques, but they can look at supermassive black hole mergers. And then finally, perhaps the most exciting thing is gravitational waves from the Big Bang. Right. The only way you can study the moment of the Big Bang is through gravitational waves. It just so happens that light couldn't escape until about 400,000 years after the Big Bang. So using detectors that are now on the South Pole, we hope, will be able to measure gravitational waves from the Big Bang. So this is an entirely new field. It's very exciting. It's wide open. We've just started. But we think the future is very bright. So let me acknowledge the fact that there are 1,000 people who contribute to this work. My team here at Caltech, this is Caltech, MIT, Hanford, and Livingston. This is the much broader LIGO scientific collaboration. And I always have to acknowledge the fact that we get our funding from the National Science Foundation, which has been a steadfast partner. This has been a very hard experiment. It's taken 40 years since we started to do it, and they have supported us all along. So I think with that, I will stop. The future is here. Gravitational wave astronomy is real. LIGO just started operating on November 30th, our second run. We're back online, so stay tuned. Thank you.